Okay, good afternoon, everyone. Thank you for attending today's webinar session on Passive House. This webinar will be recorded, and the recording is usually posted to the Code Adoption Toolkit within a couple weeks, so give us a little time there. If there are any issues with audio, feel free to write me in the chat. My name is Erica DeLello, and I'm a project manager for Noresco. I just am going to go ahead and enable that chat so you can do that. There we go. This series is sponsored by the Colorado Energy Office with training materials created by BuildTank Inc. So Robbie and I have been working with the Colorado Energy Office to provide trainings just like this one. You know, a few of you have probably been on our webinar series in the past. And so we've got the list of upcoming webinars that are over the next couple months. I'm hoping that we can continue to add to this series, so keep an eye out for an email from me. I want to take time to highlight that the role-based trainings that we also offer, and it's a more in-depth series of going over the code from the perspective of, say, an architect or a contractor or a building inspector, you name it. Any of these that are listed on the screen here, we are creating trainings for those folks to go through and apply the understanding of the IECC to an actual project, for example. So walking through a real life project example and asking questions, and so that what you're learning is really being ingrained and throughout the training for you guys. So we're offering those as well as our webinar series and the virtual or in person. If there's a specific topic as it relates to the energy code that you are interested in being trained on for your organization, we're happy to do that as well. And then of course there's all of the previous recordings that are available from this webinar series that's available on the Code Adoption Toolkit. And then Robbie actually did a few short video clips on, I think it was like HRVs versus ERVs and heat pumps. And so those are available on the Code Adoption Toolkit as well. So definitely check those out. We also offer technical assistance for code adoption. So any jurisdiction that's looking to update to the 2021 IECC or any amendments to the IECC, we're here to help. We have subject matter experts that work with you to review your current code and see how we can make amendments moving forward so it works best for your jurisdiction. And yeah, we're here to help. And this is all free to you all to utilize. So feel free to reach out to me if you guys have questions on that. So this is the Code Adoption Toolkit that I keep mentioning. You can Google Colorado Code Adoption Toolkit and it should come up. The tool that I really it has a whole bunch of different resources and information on there that's available to you guys, but the one that I really love to highlight, my favorite resource, is the helpline. And so you can submit a question on any building code and a subject matter expert will get back to you within a couple days time. So this link is available on the Code Adoption Toolkit. You can scan this here to go directly to this link as well, and make sure you bookmark it. We've seen some uptick in usability on this, and we love to see it. So it helps us to identify, future trainings and what we should be training on, as well as the post-training survey that you guys will be receiving at the end of this presentation. It'll ask you if there's other topics that you want to hear about. So definitely fill that out. It helps us to improve on these webinars. And lastly, if you have a question, go ahead and submit it in the Q&A function or in the chat. We'll also open it up to raise your hand at the end of the session, and Robbie will go ahead and take time to respond to those. So today's presenter is Robbie Schwartz. Robbie founded BuildTank Inc. to be a practical building think tank, to do research, education, and work with builders to ensure that their homes not only comply with codes and programs, but perform. So at BuildTank, they strive to use what they learn from their fieldwork to affect meaningful change in the construction industry. He's also the new homes building advisor for Boulder County's Marshall Fire. So with that, Robbie, I'm going to go ahead and stop sharing my screen and let you take it from here.
Okay. You should be able to see the screen now.
Yep, looks good.
Great. Thanks everyone for joining us today. This will be a fun presentation and the first time I've given this presentation, so you have to bear with me potentially on. I'm going to actually turn off my video at this point so that you can concentrate on the slides, and I'll come back on when we're done here. Today, again, we're talking about Passive House. And so we will talk a little bit about the story behind Passive House. We'll talk about Passive House Institute and the Passive House Institute US. There are two different versions of the Passive House kind of program. We'll talk a little bit sporadically throughout the presentation about how the ICC addresses some of the issues that Passive House is trying to address. And then ultimately, it doesn't matter if you use which standard of the Passive House standard do we use, the PHI version or the FIAS version. And we'll talk about what those things are and how they're different. But this all really started in 1977 when Howard Orr built a house on the prairies of Canada. And he was really inspired to build his house after growing up on the prairies in Canada. And he said, as a quote about this, that when I was growing up, going to public school, somebody had to get up in the middle of the night to put coal on the fire. Otherwise, we would be cold in the morning. And he really consciously decided to build the house in a different way than it's been built in the past there. And he became an architect, and he became a professor at the University of Saskatchewan. And he began to study air leakage in homes, passive solar design, and the effectiveness of insulation and the choices that we made in our houses. And his work actually, he became or was given an award called the Order of Canada for his work in homes in Canada. And that's a very prestigious award. It's almost like being knighted in the United Kingdom there. So this is the first house that he built, and it's considered kind of the first passive house in North America there. And what makes it unique at the time frame was its airtightness and combination of kind of these different things that were creating the performance of the house. It included airtightness, super insulated assemblies, heat recovery ventilation, which is very new, and all in this attempt to try to create zero energy home design there. And kind of the outcropping of this house that was first built in 1977 was the creation of the modern players in the passive house world. So in the passive house world, we know that building to passive house and building a certified passive house homes is a daunting project, or it's a serious technical challenge for a lot of us, and especially for the average home builder in North America. So understanding the requirements, the building science behind it, the design of these buildings, and how we create a building that uses next to no energy takes time to do, and it takes kind of a commitment to make it happen. What kind of further complicates this are the modern day players in this, and how we got to these modern day players. We basically, in North America here, we have three players. We have the Passive House Institute, which was the original founder of kind of the Passive House program there, which is the PHI there. And then we have the Passive House Institute United States, whoops, which I misspelled there. And then we have North American Passive House Network. And the North American Passive House Network is really the bridge between the Passive House Institute and those of us in North America that choose to use the PHI version of Passive House there. So what happened after 1977 was, in 1990, Dr. Wolfgang Feast created the Passive House Institute, or the PHI version. He did that after building the first kind of passive house in Darmstadt, Germany, using the latest building science that's out there, which really dramatically increased the building's energy efficiency substantially there. Then he built a certification system around that house and the experiences that he had building that house and some subsequent houses that came up after there. And he gained the attention of Katrina Klingenberg, who became who Dr. Feist became a mentor of. And Dr. Feist really encouraged Katrina, who was an architect at the time, to reintroduce the concepts of to North America and take the PHI program, or the Passive House Institute certification program, to North America, which she did do there. So when we begin to define what Passive House is, and we begin this journey from Europe to the United States, we begin to realize that there are kind of two characteristics that we're really dealing with. We're dealing with understanding thermal comfort of the indoor environment, specifically, and how to significantly lower operating energy as compared to what's being used in existing homes there, and ensuring that these two principles that are defining Passive House are carried out, and how we're ultimately going to carry out those versions here. So the PHI, or the Passive House Institute, has created kind of some guiding principles here. The first one basically talks about reducing loss through the building envelope. So understanding how to build a home with thermal bridge-free construction, super insulated building envelopes, airtight construction, and then applying building science to this type of construction techniques, so that we don't have houses that fail quickly, but are continuing to be long-lasting and durable houses. You might remember some of the construction that was happening in the late 70s and early 80s, where we were building houses that basically failed within a few years after building them, because we are building houses and kind of changing the way that we build houses to meet people's modern day expectations of comfort and durability and efficiency there. But we didn't always incorporate the applied building science that needed to happen. So that is a really big point of this idea of passive building, is understanding the building science behind how we put things together. Second, we're talking about optimizing the balance of energy gain. So we're talking about not just willy-nilly adding windows to the building to take advantage just of views or architectural appeal of the house, but really strategically placing windows in the house to get that architectural appeal, to take advantage of light and connection between in and outside, but do it in the best possible way, so that we can also optimize solar heat gain and minimize any overheating that the building might have, which might mean that we have to also think about window shading specifically there. So that's the real Passive House side of things. So what I should say real quickly here is that there is a difference between the Passive House philosophy and passive solar design, or passive solar gain. Passive House kind of incorporates passive solar design, but Passive House is really a bigger principle that's trying to reduce the heating and cooling loads of our houses substantially by incorporating other things than just access to the free energy of the sun there. The third thing is efficient systems. So how do we choose and install highly efficient mechanical systems in our houses, which include, all of those things from general appliances, heating and cooling systems, water heating systems, as well as air exchange. So how whole house controlled mechanical ventilation, as well as spot ventilation, becomes kind of crucial things that we need to think about in much more depth as we're tightening up the building envelope and creating much more greater efficiency through that building envelope. And then we have thermal insulation. The opaque building components of the exterior envelope have to be well insulated. It doesn't necessarily mean that we're only relying on moving insulation from the cavity to the exterior, but we have to understand what happens when we build a super insulated structure and we don't have exterior continuous insulation? How are we going to make that assembly work and work well from a building science perspective? And then lastly, we have air tightness of the building thermal envelope. And you see here that the target is 0.6 air changes per hour at 50 pascals of pressure. And you have to verify that or confirm that with blower door testing by doing both a pressurization and a depressurization test. And it's got to pass both of those. So air tightness is crucial. And as we've learned with the energy codes, roughly, half of the energy conducts out of the building through our building assemblies, from energy moving from higher concentrations to lower concentrations. And another portion of that energy, or the other half of the energy or more, is leaving the house through air leakage or through being carried with air. So air is a great transport mechanism for heat, but we have to also remember that it's a great transportation mechanism for moisture in our houses as well. So air carries heat and moisture, and we need to gain control and predictability of that airflow in order to create a house that is highly efficient, but also is highly durable, that's going to last over time there. The building principles continue with ventilation and heat recovery here. So we want to create good whole house controlled mechanical ventilation. And as you'll notice in the IECC, it also incorporates house tightness and ventilation. So that sound building science principle of building tight and ventilating right, and then mitigation of thermal bridging is kind of the last thing here that we're going to talk about. And I guess the passive house windows as well. Again, looking at windows themselves, when we look at R values, we're looking at the component R values, so the cavity insulation as a component there. When we start looking at windows or start thinking about U values of assemblies, we're starting to talk about the assembly as a whole there. And when we look at a well-insulated wall, for example, I might say that I'm building my wall with an R30 cavity insulation. Well, what is the actual R value of that whole assembly there? When we take the R value and we incorporate the framing and the windows and whatnot, that R30 is dropped, almost in half, depending on how we build our assemblies and if we're taking into account thermal bridging and the requirements of the windows. So windows have a huge impact on our houses, not only the quantity of windows, but the U value of that assembly of the window, not just the center of glass, but the frame and the low E coatings and the edge spacers create the total U value of that assembly there. And Passive House really requires a much more higher performing window than we typically would see within the IECC, because we're trying to regulate and control the energy flow through that building envelope, and that energy flow as a nominal or as a whole wall R value, not just the components there. So we need to think about things as assemblies and how they perform as assemblies. So ultimately, we're actually talking about the U value of that assembly rather than the R value of that assembly. So what PHI really did, or the Passive House Institute really did for us, is introduce the idea of performance requirements or benchmarks versus prescriptive requirements. So you'll see here the performance requirements, and the IECC is kind of getting at those same performance requirements, but they're doing it from the perspective of prescriptive requirements. So a prescriptive R value requirement in our wall to achieve a heating demand load there. So when we go through these Passive House criteria, we see that the heating demand, it cannot exceed 15 kilowatt hours annually, or 10 kilowatt hours peak demand per square meter of usable living space. And the cooling demand here is roughly matches the heating demand with an additional climate-dependent allowance for dehumidification. Now, in our climate zone here in Colorado, we don't need a lot of dehumidification, But what we're seeing in other climate zones is that we not only have to have cooling, but we also have to have separate and independent dehumidification systems in these tighter, well-insulated homes there. Air tightness has a maximum threshold, as I said before, of 0.6 air changes per hour at 50 pascals of pressure. So it's using the air change per hour metric in this traditional or fundamental starting point of the Passive House Institute program. The primary energy demand there is looking at the renewable primary energy, or the PER, and it cannot exceed 120 kilowatt hours annually for all domestic appliances, which would include your heating and cooling appliances, hot water, domestic electricity, and all of those things. And it's based on a per square meter of usable living space a metric there. So you'll see that in the PHI version of Passive House, that most of the things are based off of a metric that's using a square footage of the home as its energy placard there, I guess. So it's kilowatt per hour per meter squared of conditioned floor area there. So these criteria are just spelled out again here. We have the space heating energy demand that I just went over, the space cooling demand, which is roughly matches the heating demand there, renewable primary energy demand, which is based off of a certain kilowatt hour per square meter of treated floor area per year. We have that air tightness limit and the thermal comfort perspective as well, which is something that's kind of added here. So the thermal comfort perspective is trying to provide in the living areas during the winter and summer months that your temperature change in those areas isn't dramatic. It's not more than 10% of the hours in any given year over 25 degrees Celsius here. So this was, this kind of brings up one of the issues between bringing the Passive House Institute standards to the United States. They're using a metric system, and we use we don't use the metric system ultimately here. We didn't follow through on Jimmy Carter's desire to move us to the metric system here. But what we see with this criteria is that we're achieving this through intelligent design and implementation of these building principles in a planned and optimized and also verified way. And we're using software to start generating ideas of how these homes are actually going to perform. So that becomes a very important part of the puzzle, is to ensure that we're doing that software modeling and planning before we're building these houses, to ensure that we can execute it in a way that will ensure that the house lasts over time and will be a long, durable house here. So the PHI, or the Passive House Institute program, has its core standard there, but it also has realized that a lot of people who are building to certify their houses aren't always able to achieve that level of performance. And one of the areas where they really struggle often is getting that 0.6 air changes per hour. So they've come up with the Passive House Institute low energy building standard, which backs off on some of these requirements for the traditional Passive House Institute requirements to get certified under that. And you can see that one of the things that they backed off is from the 0.6 air changes to 1 air change per hour there to make sure that it works. And so you can still certify the house, but you're certifying it under a slightly different and slightly less aggressive energy standard when you're using the low energy building standard. The certification process here is important, and really requires that you start working with a certified Passive House designer and also a certified Passive House consultant. Now, sometimes that individual will hold both of those roles, but the consultant is crucial to bring in early and as early as possible. In that process, you're really building a team to build this house. So you have to not only have the consultant, but a builder that's willing to do this, and the consultant and the builder working together to specify the components and the energy features in that house. All the energy relevant planning documents have to be created, and the technical data are submitted. And ultimately, the certifier is taking a look at that before the house gets built at all. If any specification changes are made, they need to be made before the house is actually built there. And then after completion of the construction, if any field changes are made in the field, maybe you couldn't get the specific passive house window that you wanted there, then you have to go back and you have to put that data into the software packages here and ensure that you're still meeting the criteria. And the passive house consultant might do the energy modeling, and then it's got to be certified again through the passive house certified designer there. And so we want to make sure that this certification process happens well, and that it happens at the beginning of the process and throughout the process there. Now, one of the things that you'll see that is a little bit different in the two versions is how are things field verified. It's spelled, you'll see here in a few minutes that the Passive House Institute US version of the program really spells out how field verification happens. It's not spelled out as well in the Passive House or the PHI version of the program here. The consultants and the certifiers might go out and do some of that work, but they're not required necessarily to do that work. So maybe an energy rater will go out and do the blower door testing for that house, but is anybody actually looking at the structure and how the structure was built, and does the structure match the design there, and those types of things. So that is one thing to keep in mind, and it'll come up again as we move through towards the FIAS version of the program. But the certification review process kind of looks like this, where you're beginning with this preliminary review, and then the design stage review and the construction review. And then you ultimately get down to the certification. And then you have kind of these optional inspections with additional review, analysis, and then the blower door testing. So a lot of this optional inspection, what they call optional inspection, I added /analysis because a lot of it is really in-office analysis rather than on-site field inspection that's happening out there when you're using the PHI version, and or that on-site inspection, it seems to be optional, not required there. 5 reasons to hire that Passive House certifier and consultant and get that team working together is that you do get independent review. They do look at the design of the assembly and how, from a building science perspective, if it's carried out as designed, will it work? Will it prevent condensation? Will it prevent other things that may cause that assembly to fail? And will it also achieve the energy and performance goals, the comfort goals for that particular house? You can avoid false starts by getting these consultants involved early in the design process of that house. You can also help to develop the teams. So bringing in the framer, bringing in the insulator, having them understand what the Passive House principles are and how to actually execute them, understand that they really need to read and understand the plan set and the design characteristics of that house, the design details of that house, and how to carry that out. And then a big part of the Passive House is trying to control costs. So figuring out the most cost-effective ways to build that house is going to be crucial as well. So, and those are all things that the certifier and the Passive House consultants can help people understand here. What we do see with regards to the Passive House Institute standards is that it is kind of a one-size-fits-all set of standards that are for every house in the world. if you're building to the PHI standard. So that's one of the big things that we see was looked at when Passive House came back over to the United States and North America. That didn't make a lot of sense. So we see that Passive House in North America, that the methodology needed to be adapted slightly for the North American market. You know, the first thing that needed to be adapted was changing its software package, which is the PHPP, or the Passive House Planning Package, needed to be changed from a metric system to an imperial unit system. And as soon as that was done, you really saw a boost in the popularity of the program there. And then Katrina Klingenberg and others launched this collaboration with the Department of Energy and Building Science Corporation and some other folks there. And they realized that the North American climate realities were very different than the German climate zone. And so that one size, didn't necessarily fit all of North America there. And we'll get into that in just a few minutes here. Unfortunately, Passive House Institute was not very excited about changing things or collaborating to see how to convert or deviate from their standards there in other countries. And North America and the US version really continued down this road. And finally, in 2011, the Passive House Institute cut their official tie and connection with Passive House Institute US. And so hence now we have two versions of Passive House that are being used in the United States. One is the European version, or the PHI version. One is the US version, or the PHI US, or FIAS of the standard here. And so to go into a little bit more about the FIAS approach here versus the PHI approach, we have to realize that, yes, it's starting with the PHI approach, but they realized pretty quickly that different climates had different combinations of heating and cooling requirements, and therefore that one size fits all approach wasn't going to work well in the United States here. And so they really were seeking a more precise and informed design guidance to be able to create energy targets that actually made sense within the United States versus that one size fits all kind of metric there. And this is kind of an example of that. We see that we have Juneau, Alaska versus El Paso, Texas. And you'll see that the FIAS version is based off of conditioned floor area potentially, as well as the PHI version, but the results are pretty different. You don't necessarily have to understand the results, but you'll see that the heating demand in Juneau, Alaska on the FIAS version is 26 versus 15 in the PHI version for Juneau, Alaska, as well as 15 for El Paso, Texas, when the FIAS version is kind of right-sizing the equipment, right-sizing the building envelope for that specific climate. And you're seeing that we get a 6 in the heating demand. So it'd be 6 kilowatts per meter squared in El Paso, Texas there. So the FIAS standard is now, the one that we're using now is the FIAS 2021 standard. It's that's the most recent release. Just like code development, they developed the FIAS standard, and it started out, I think the first one that was published was in 2018, and then they came out with the 2021 version there. It aims to consistently deliver, on the bullseye, meaning that we're trying to optimize for that particular climate. So we have optimal envelope design, cost effectiveness, building science-based details that will get us comfort, durability, and efficiency. And it's very sensitive to the typology of the house, which means that the configuration, the dimensions of that house, how big it is, how complicated the building envelope is of that house. And then it also is taking into account occupancy, which the PHI version has not taken into account. So we're really, again, getting that fine tune, hitting the sweet spot for the specific climate that we're working with there. The core building principles are very similar to the PHI version. We have the high performance building thermal envelope. We have the thermal bridge free or reduced thermal bridging in our houses. Ideally, we're going to eliminate it, but there's realization that it's not always able to eliminate the thermal bridging. So at least you're required to minimize it as much as possible. Air tightness is super critical here. But they do look at air tightness slightly differently. We'll get to balanced ventilation systems with heat recovery. That sound building science principle of building tight and ventilating right equals better indoor air quality, but it also helps us with moisture control in our houses there. High performance windows, similar to the PHI version. Again, realizing that windows are our weakest link. So we need to be really conscious about each window placement, how much window to wall area we're getting, how we're going to shade those windows, how we're going to optimize the solar heat gain, but not overheat our houses as well, which gets us into that shading and daylighting. And then moisture management is specifically called out as a core principle in the FIAS version. It's basically implied in the PHI version there, but it's not, as far as I can tell, it's not specifically called out as a core building principle in the PHI version. And then active conservation. So it's kind of shifting a focus to lighting appliances, mechanical systems, and other equipment, as well as EV charging, and ensuring that we're setting ourselves up to potentially get to zero energy in these passive houses. Passive house doesn't equate or mean zero energy homes, but that move to zero energy homes often can be much easier than it could using either of the two versions, the PHI or the FIAS version. It's going to be easier to get to zero in those houses. So kind of delving into the more moisture management side of the equation within the FIAS program, they have 3 compliance pathways that we can look at. First option is to follow kind of a prescriptive building science-based guideline for vapor control management. It's kind of very similar to what the code is doing, and we'll talk about that in essence here in a second here. You could also do a WUFI hydrothermal analysis of the house and of the assembly to see what the potential for moisture condensation is within that assembly. The one downside from my perspective, and this is maybe just my personal view here, is that the WUFI analysis always assumes that there's moisture in the assembly. And if there's moisture in the assembly, what is it going to take to get that moisture to condense, to change from a vapor to a liquid in that assembly? And when it gets to its liquid state, that's when it's really going to be a problem there. So from my perspective, we're designing these assemblies. We should be designing them so that moisture isn't going to get into those assemblies. And if it does get into that assembly, we always have that drying potential there. So I personally believe that there's some downside to the WUFI hydrothermal analysis, and or the third option, which is allowing an engineer design a qualifying moisture assembly that is taking into account there, because the engineer and or the WUFI analysis might be concentrating too much on moisture getting into the assembly, and what do we do once it gets into the assembly, rather than preventing moisture from getting into that assembly as well there. But anyway, the FIAS also provides some guidance on interior surface temperature requirements and construction details that control the interior surface temperature of these assemblies, because we know that condensation is created by 2 things. We have to have potentially elevated relative humidity or vapor in the air, and then we have to have cold temperatures where that condensation, that warm moist air is going to hit, and then condensation will take place here. So when we're talking about this and kind of in relationship to what the IACC is doing, we see that the IACC is really focusing on the vapor retarder. And what we know about the vapor retarder is that it's trying to stop the process of diffusion. And diffusion, as described in picture on the right here, is basically the process of moisture in its vapor state moving from higher concentrations to lower concentrations directly through the pores of the assemblies that we're building with. So in Colorado, we're talking about most often it's moving from inside the house where it has higher concentrations to outside the house where it's lower concentrations. And it has to go through the pores of the drywall into the assembly and then get to the exterior surface where it might condense and ultimately diffuse to the exterior of the house there. What we know from the studies that have been done on this process and are depicted in the diagram on the left here is that moisture diffusion over the course of the winter season is a very small process of moisture migration. And in this case, over the course of the heating season, only a third of a quart of water was able to migrate through the wall assembly here. But on the flip side, if I introduced 1 square inch of hole area, I get 30 quarts of water that are able to migrate into the assembly with air. So one of the great things that Passive House is doing is bringing up this real recognition that moisture moves not only by diffusion, but also with air, and we need to control both of the equations here. Whereas code, is still allowing 3 air changes per hour, which is good, roughly good from the perspective of energy, potentially, it's better than it was before, but it doesn't take into account the amount of moisture that's moving with 3 air changes per hour and trying to keep that out of our homes here. So when we're building a thicker wall assembly here, the picture on the left here is showing that in our traditional 2x6 assembly, we have a certain amount of heat flow from inside, or I guess we would say just across the assembly from higher concentrations to lower concentrations. And we aren't retarding or reducing the amount of heat load as much as we would with a thicker assembly. So that's why the arrow on the right side is still pretty red there, because a lot of energy is still going through that assembly, which means that the exterior surface temperature is still pretty high there. As we build thicker and thicker assemblies, the exterior temperature starts to cool. The exterior sheathing starts to cool more and more. And so it's trying to depict there that less energy is moving from one side of the assembly to the other side of the assembly. And therefore that surface temperature is colder, and we potentially have a higher risk of condensation on that colder surface temperature there. So what Passive House is doing is really trying to ensure that this doesn't happen, that we don't get condensation on that first condensing surface or that cold surface there. And they're doing it by controlling air leakage, which is a big transport mechanism for moisture. So we're building that super tight, airtight assembly, but we're also getting a vapor retarder in the assembly. And we're also adding some continuous layer of insulation to help warm the surface or get better control of the heat that's moving from inside to outside in our assemblies there. So it's taking account of 3 things where, and in conjunction with each other, in synergy with each other, whereas the code is primarily looking at the vapor retarder as its primary means of looking at how moisture can be managed in our wall assemblies there. So we might get condensation on that exterior surface. And just as an example of how that condensation happens, if I have air that's at 35% relative humidity and it's at 70 degrees temperature, this chart, this is an abbreviated psychrometric chart, it demonstrates that if that air at 35% relative humidity and 70 degrees hits any surface temperature that's at 40 degrees or less, we're going to get condensation being formed there. So it's crucial that we keep that moisture out of these assemblies, and therefore we're relying on really sound building science-based, applied building science building practices there, so that we have assemblies that have air barriers and also vapor retarders in those assemblies so that we don't get vapor retarders that get bypassed by air leakage. And when that happens, often the vapor retarder is such a vapor retarder that it traps the moisture in the assembly rather than allowing that moisture to dry back out of that assembly there. And that's obviously something that we don't want. So from an IECC perspective, it's promoting drying of the assembly and not using that class 3 vapor or class 1 vapor retarder that might trap moisture in the assembly. It's instead taking us down the road of using a class 3 vapor retarder that has up to 10 perms of permeability or ability to allow moisture to move through it. But when we do that, we have to either have a ventilated cladding on the outside or continuous insulation on the outside to warm that exterior cold surface so that it's not going to create condensation inside that cavity. And ideally, we would actually have assemblies that have both a ventilated cladding and continuous insulation on the outside. So we're promoting drying there, but we're also promoting not getting condensation on that first condensing surface there. From a passive house perspective, instead of going to a class 3 vapor retarder, they're using the vapor retarder as also their primary interior air barrier control layer. And so they're using these smart vapor retarders / air control layers in the houses. And there are these systems like Intello and Myrex, and even CertainTeed's membrane could be used if we install them properly. The problem with most vapor retarders is that they're not installed. There's no installation instructions from manufacturers of how to install a piece of poly as a vapor retarder in our houses. But we know that it can be done well because in Minnesota, for example, they're actually installing it well, and it's acting as a primary air barrier on the inside as well. If it's not installed well, you get moisture bypassing the vapor retarder with air leakage, and we get that problem here. So you'll see kind of the picture here where all the seams are taped and sealed around window openings, around connections and joints in the assembly. It all needs to be sealed so that it's airtight, so that moisture with air is not going to bypass these systems here. So enough on that. Let's move on to window comfort criteria. So windows are another place where you're going to potentially get condensation on that window if the R value or U value of that window assembly is not good enough to create a surface temperature on that window. In the example that I gave, that surface temperature had to be in excess of 40 degrees to ensure that air that's at 35% relative humidity and 70% or 70 degrees temperature doesn't create condensation on that glass there. So the FIAS system has some window comfort criterias that would dictate the U value of the window that we have to achieve. And so it's from a comfort perspective, but it's also from a condensation perspective. You know, regardless, windows are going to be have less R value in essence than the wall assembly there. So our body heat is going to radiate to that window, and we're going to feel a little bit uncomfortable. But the FIAS system is trying to regulate that to an extent where we ensure that the surface temperature is such that less of our body temperature is going to radiate to that surface. And because of that, we're also going to get less condensation or moisture buildup on that window surface there. So that's an important thing. Also, it deals with combustion of fireplaces and safety. It doesn't disallow the use of atmospherically vented fireplaces or wood burning fireplaces there, but it does say that if you're going to use a wood fireplace in order to continue to have a super rock solid building thermal envelope and an airtight building thermal envelope, you do have to have a sealed combustion, in essence, burning fireplaces, which means that the doors need to be airtight and sealed, and you need to bring combustion air directly from the outside to the firebox itself in order to maintain that flame and to get drafting of the byproducts of combustion up and out of the house there, and without having interaction with the air in that house. So you're just getting the benefit of the heat from the fireplace. You're not getting the benefit of air in the house being used as combustion air and then just being drafted out of the house as well there. FIAS Core, their core principle, can be implemented using a performance approach similar to PHI, or they have just created a more prescriptive approach. And I would say that it's kind of a quasi-prescriptive approach, because you see the spreadsheet or the colorful document on the right here. That's the prescriptive kind of checklist for the FIAS program. It can only be used for single-family dwellings or that are detached or attached single-family homes. But this spreadsheet here, in essence, is basically a reduced, less detailed modeling approach there. And because of that, there's some limitations to the ability to use the prescriptive approach. For example, the window to floor ratio in the area of the bedrooms are limited window and skylight areas, and actually orientation of those windows, and compactness or the building form, how much surface area of the building thermal envelope is there, is limited when using the FIAS Core prescriptive approach to certifying a home under the FIAS standard there. This allows you, however, to improve your budget, I guess, so that you are not spending as much on the detailed energy modeling that our approach that you would have to use, and it would lend you to using the more prescriptive approach for moisture management and those types of things, so that you're still getting a sound building thermal envelope that's going to be durable and not be susceptible to condensation and moisture damage, but in a more cost-effective way to be able to do that there. The FIAS Core, again, has some other requirements there that are required whether you're using the performance approach or the prescriptive approach. They do allow fossil fuel appliances in that, but they also require electric readiness to be installed there. They also have zero energy focus and require compliance with the DOE Zero Energy Ready Homes program as well. And then renewables are not required, but there are some load reduction and load flexibility things that would ultimately lead you to adding renewables to the program there. As I said before, the PHI version of the program doesn't really spell out well third-party verification and inspection. And I would say that the FIAS version does spell that out really well. They do require that you have third-party inspection and verification. It's conducted, and they have a designation and a training and certification for a certified FIAS rater that would go out and do inspection during construction of the process there. And then again, they should be brought in early in the design process as well as the design consultant there. The verifier it's called something different for multifamily and non-residential buildings, because you can certify commercial buildings as well as multifamily buildings. That certifier would be called a certifier versus a rater there. And you can see some of the things that the certifier or rater would be looking at and the inspections that they would be going through. This is really probably most specific to the single family realm there with regards to whole building air tightness testing, room by room pressure balancing for sure. That's a requirement of the DOE Zero Energy Ready Home program that's been incorporated in there. But you need to look at all these things and test it and verify it, and not only do it at the end of construction, but do foundation and pre-drywall inspections as well. I mentioned electric readiness. So again, they allow fossil fuel combustion mechanical system to be installed, but they also require electric readiness requirements for combustion systems, water heating, clothes drying, cooking. So in essence, you have to pre-wire these systems or these areas so that sometime in the future you can switch over to electric appliances, which often are significantly more efficient than their gas counterparts there. Which leads us to FIAS Zero. The PHI program really is setting you up to get to zero energy. The FIAS program has created another designation, the FIAS Zero or Path to Zero Energy program there, which builds on the FIAS core requirements that we've talked about, but allows either on-site or off-site renewable energy to get that house to zero there. The other thing that they've done by incorporating the DOE Zero Energy Ready Home program is to ensure that all of the characteristics of the Passive House program are carried out to such an extent that you are really ready to put on renewables onto that house to take it to zero. So just like any program, if you're trying to define zero energy using an energy rating index score, a passive house or any other type of code built house or any type of house out there could only achieve an energy rating index of about 30 to 35 if you've maximized the building thermal envelope and the mechanical efficiencies of that house. To get from that 30 to 35 to zero using the energy rating index scale, that is all taken into account by adding renewables to the assembly there. So when you're building a passive house and trying to get to zero, you basically are really getting to that 30 energy rating index score, that 30 to 35 energy rating index score. So you basically have to put on less renewables. It's more cost effective. Whereas the true DOE Zero Energy Ready Home program, you could still meet the requirements of that program and be ready to go to zero with an energy rating index score of around 50 versus 30. So you're going to have to add more renewables to that house than you would a passive house there. But they have partnered with the Department of Energy there, so you can get that DOE Zero Energy Ready certification. And it turns out that the Zero Energy Ready Home program also incorporates Energy Star for homes. So you're going to get an Energy Star certification as well as an Indoor Air Plus program certification. So you'll have all of these certifications plus an energy rating index score coming out of the process of the FIAS program. With the PHI program, you don't get all of that additional kind of marketing benefit if you're a builder, but also certification and assurance that third-party verification is happening out in the field there. The other thing I wanted to point out is that the PHI version talks a lot about healthy indoor environment. And it primarily talks about that from the building science principle of building tight and ventilating right and requiring balanced ventilation strategies that have some ability to transport energy from the outgoing airstream to the ingoing airstream. FIAS talks about it kind of in that same way, but it adds in the Indoor Air Plus program, which is an Environmental Protection Agency program that talks about material selection. It talks about radon. It talks about moisture management in a more kind of robust way. All of these things that can degrade the indoor air quality of that house are being addressed that goes beyond just ventilating the house. Ventilation is part of an indoor air solution for that house, but we also need to ensure that we're getting we're looking at the materials that we're bringing in, that they don't have volatile organic compounds and those types of things. So I need to speed up here real quick to get done here. We have the PHI versus FIAS, is one better than the other? I'm not sure that one is better than the other. I think that people have personal preferences between one and the other. My personal preference is the FIAS system. It makes total sense to me that we should have climate-specific requirements versus a one-size-fits-all strategy. I also like that what I was just talking about, the indoor air quality part, that it's a little bit more focused on that in these super tight structures and whatnot. You can get new construction certifications from FIAS with FIAS Core, FIAS Zero. With PHI, you have the Passive House standard for new construction, or you have the low energy building standard. And PHI and FIAS both have existing home retrofit programs, which basically means you have to take it down to the studs and rebuild the house in order to make it work there. The other thing both systems require is in-depth and detailed energy modeling. FIAS uses a WUFI hydrothermic or WUFI passive house tool that includes the WUFI hydrothermic analysis as an option you can use always. And PHI uses what's called the passive house planning package, which is in essence a huge spreadsheet that has been developed to look at all of this, all of these issues there to get certification there. Heating and cooling criteria, FIAS is based on an envelope area, floor area, and also adds in occupant density and also the climate locations, where PHI has the same heating and cooling loads for all climates worldwide there. And one of the things that this brings up is kind of the question of how do we integrate HVAC design and the IECC HVAC design criteria into Passive House. So Passive House doesn't do HVAC design in accordance to ACA standards there. They do calculate the heating and cooling loads, which is similar to the Manual J, but how the equipment is selected to meet that has the capacity to meet those loads, and how ducts are designed or distribution systems are designed is really kind of not in alignment with how the code is doing things. So you're going to have to come to a choice if you're a code official, how you're going to make that work with it. You might have to actually force them to do an HVAC design using ACA Manual J's, and ACA manuals have just come out with a low load Manual J system, and I don't know how it compares with the Passive House design softwares, but I would imagine that it's closer anyway there. Or your other choice is to just rely on the design softwares that the Passive House programs are using and assume that it's better than the ACA system for designing there. Air tightness, they do have different metrics. One is an air change per hour metric. One is a CFM per square foot of envelope area. And one analogy that was made there that makes sense to me why the CFM per square foot of building envelope makes more sense is that you wouldn't estimate the gallons of paint that you need for your wall system by measuring the volume of the house. And it's kind of the same thing. Like paint, when it comes to air leakage, it's all about the surface area of the building and how many holes are in the building there. So I really like the CFM per square foot of envelope area metric better than the ACH metric there. And you'll see that we've been able to get that metric in the code as a beginning kind of step in this exceptions for smaller buildings than bigger buildings and or attached buildings there. And our hope is that over time we can kind of replace the air change metric in the IECC with a CFM per square foot metric there. Energy use. So the other thing that FIAS does is it really adds the occupant factor into the equation here versus just looking at a square foot metric for energy calculations there. And you can see in the graph below that it does make a difference, but is that difference enough to really change things? And is it different enough to make a big difference in it? or, I guess the other thing I'm trying to say is that the climate specificity of the FIAS program might be also the other thing that's causing that those differences in the energy demands that are required here. This is just a quick Passive House PHI comparison. You can see that, really they're trying to do the same thing. They are taking into account source energy a little bit differently. Source energy is the realization of where the energy is actually created in our houses, and the realization that for every 3 kilowatts that leave a power plant, only 1 actually makes it to the house. So the FIAS has created a ratio that calculates the ratio of what they call the source energy factor. And PHI has done that as well. But because PHI calculation is a little bit differently, and it's the same ratio worldwide, they're basically saying that houses in North America are 20% cleaner, that the source energy is 20% cleaner than it actually is there. So again, I think getting to that climate specificity can make a difference. And this just is an example comparison between the PHI and the FIAS with regards to the source energy limits there. You can see that the PHI standard uses 120 kilowatt hours per square meter, where the FIAS standard is looking at a kilowatt hour per person per year metric that would be specific for a specific climate zone there. And this comparison kind of takes it into a little bit more depth. So you see the two that are highlighted in blue are in Denver. And you see, if you go down to the second square there, I changed the occupants there. So I went from 4 occupants to 6 occupants. And you can see that it ultimately, the bottom square there, it changes the kilowatts per person per year. And then I did the same thing in Denver versus Leadville. And you can see that not only the occupants change is an issue, but the climate is also an issue there as well. So you'll take a look at that in the space conditioning criteria there. So these slides will be available. You can look at them. I'm trying to hurry through here so we can get through. PHI calculates the treated floor area. FIAS calculates the interior conditioned floor area. They're basically doing it the same way. And Passive House, the last thing that I'm really going to talk about is that Passive House criteria also is beginning to certify products as well. And the way that the certification process works for different products is a little bit different for each of the systems. And the FIAS system is leveraging the Home Ventilation Institute, which is something that's specific to North America there. And again, getting more specificity to our specific climates and how things are working in North America makes sense to me. So again, I tend to prefer the FIAS version of Passive House for North America here. So to conclude, performance versus prescriptive as defined by the IECC, I think that's one of the biggest things that a Passive House is bringing to our recognition, that maybe it makes sense to bring more performance characteristics into the IECC instead of just relying on prescriptive mandates. You have to do X, Y, and Z. How about creating performance metrics and leaving the design of the assembly more up to the designer there to read those things? We do see that we want that robust energy modeling, and that the IECC performance approaches are starting to integrate more robust energy modeling there. Even more important is the integration with sound building science there. And we also see that as a good thing for the IECC as well, that they are integrating sound building science into a lot of the requirements. Ultimately, I don't think it matters that much which version you use. It does come down to personal preference. And again, my preference, I think, is for the FIAS version, and how to move forward with integrated Passive House buildings and the IECC. I think that's still going to be a struggle for us. You see that exemplified just a little bit with regards to HVAC design. But if somebody is building a Passive House, how do we actually determine that? Can we just make the assumption that they're meeting all the requirements of the IECC or not there? They might be, they might not be. Most likely they are, but again, getting that integration makes it more difficult there. Sorry, I went a little bit long here. That's the struggle of doing a presentation for the first time there. But if you have any other questions, I'm happy to stick around, and or you can or contact me.
Thanks so much, Robbie. Yeah, I know it's always hard to estimate the timing there. So we did get a couple of questions that came in, so we will go ahead and answer those. And then if you guys have further questions, feel free to reach out to Robbie or I, or use that helpline as well. So the first question that came in was, does PER include EV charging?
So the PHI version doesn't include EV charging. I believe that the FIAS version is beginning to include EV charging in their the 2021 version.
Perfect. Thanks, Robbie. Next question is there a cost difference between the FIAS core certification versus FIAS passive certification? Do you have any idea?
My understanding is that FIAS core and FIAS passive are basically the same thing. Core is their core certification. So there wouldn't be any difference there. There could be a little there. There isn't much difference in the cost from FIAS versus PHI certification. Where there is some cost savings is if you are doing a single family dwelling unit and you can utilize the prescriptive approach, there will be some cost savings there, primarily from the energy modeling and consulting requirements there.
Perfect. Okay, well, with that, we will let you all go. And of course, we hope to see you guys at the next session, which I believe is in a few weeks. So thanks again, Robbie, and thanks to everyone for attending.
Thank you.